There are a lot of occasions in combinatorics when one's working on a problem and one needs various sort of basic estimates. And often the bounds that one wants for different quantities can be quite crude, or rather what I'm saying, quite crude bounds can suffice. So I want to spend a little while just talking about some of the basic bounds that are used over and over again. In each case, there are more accurate bounds available if you really need them, but for a lot of purposes, these ones are okay. And what's nice about the basic bounds is that they tend to have quite simple proofs. So I'm going to start with just talking about a bound for n factorial. Of course, you'll have heard of Stirling's formula, and so you can just, if you want to, you can just look that up. But I think it's quite nice to, and quote it, but it's quite nice to know upper and lower bounds that can be proved by very simple arguments or pretty simple arguments. So, I mean, actually the idea that I'm about to say for n factorial is part of the idea for how to prove Stirling's formula, but I'm having a small technical problem. Okay. See if that helps. I'm just trying to get a thicker pen, but every time I try to do it, the window something gets in the way. Right, oh, here we go. Sorry about this little, but it will be worth it. There we are. So let's see if I end out that right. I've got a nice dark pen now. So how can we estimate n factorial? Well, the main trick is to look at the log of n factorial. So what is log of n factorial? It's just log of 1 plus log 2. Log of 1 is 0, so I needn't really have written that, but plus log of n. And if we want to estimate that, we can do it by sandwiching it between a pair of integrals. So we just say, supposing I look at the graph of log n, so I'll just look at the positive part. It crosses the axis at 1, and let's just mark some points here. So now here we have, that wasn't very well drawn. I really want to mark points on the x-axis. So we have 2, 3, 4. So there's log 2, log 3, log 4, and so on. And now if I want to write something down here that has the value log 1 plus log 2 plus up to log n, I can just put some rectangles. Here's a rectangle of height 0. There's a rectangle of height log 2, rectangle of height log 3. And what I'm getting is a lower sum for this integral where the dissection of 1 up to, well, how far do I have to go? I have to go up to n plus 1. And then that will be n. So we get that log n factorial is less than or equal to, by just looking at this diagram, the integral from 1 to n plus 1 of x to the minus 1 dx, log x dx, which is x log x minus x from 1 to n plus 1. And so we get n plus 1 log n plus 1 minus, well, we get 0 for that. And then we'll have minus n plus 1 plus 1, so minus n. And So when I take n factorial, that gives us an upper bound of, so e to the n plus 1 log n plus 1 is just n plus 1 to the n plus 1 times e to the minus n. And I'd rather write that in terms of n, so I'll call that n times n to the n times 1 plus 1 over n to the n plus 1 times e to the minus n. And 1 plus 1 over n to the n plus 1, that's less than or equal to n times n to the n times e to the, times e, sorry. I suppose I have to have a 1 plus 1 over n in there as well, so I better change that n into an n plus 1 times e to the minus n. So up to a sort of polynomial factor, which is often not very important, we get the estimate n over e to the n. But if we want an actual upper bound, we have to multiply that by n plus 1. And what about a lower bound? We can do that by exactly the same method, but now we look at the upper sum for this. Sorry, I've got an upper bound, so I now want a lower bound. So I'm going to go, I've now written something else with area log n factorial, because I've got log of 2 plus log of 3 plus all the way up to log of n minus, up to log of n. And so we get that log n factorial is greater than or equal to the integral from 1 to n minus 1, it's just up to n, I mean, of log x dx. So this is slightly nicer. So again, it's x log x minus x, but now the limits are n and 1. So we get n log n minus n plus 1. So taking x for both sides, n factorial is greater than or equal to n to the n times e to the minus n times e, which, let's forget that e, because I don't really, it's bigger than or equal to n over e to the n. If you really like that extra e, then fine, you can have it. So up to this n plus 1 factor, n factorial is around about n over e to the n. Stirling's formula will actually tell you it's somewhere in between. It's more like root n times this thing, but with an absolute constant. If you want to prove that, one way of doing it is not to use upper and lower sums like this, but to do a sort of linear bit like that. If you try and work out what you get, then you'll get the root n coming out that way, but we won't need that in this course. So there's n factorial. So the main takeaway message is n over e to the n is a pretty good approximation for n factorial for many purposes, but not for all purposes. So for example, supposing, as we often do, we wanted to get an idea of the rough size of the binomial coefficient n choose n over 2. So that gives us, so if we look at it exactly, it's n factorial over n over 2 factorial squared. But if we're sort of possibly a factor n out for each of these three numbers, then this whole thing could be a factor n out. And it turns out that being a factor n out here can mean that all you end up proving is for an upper bound is that this is at most 2 to the n, which is not very interesting because the sum of all the binomial coefficients is 2 to the n. So just using this bound here is a bit too crude to get a decent bound for n choose n over 2. Though if you use Stirling's formula, you do get a reasonable bound. But without using Stirling's formula, let's see what we can do here. So what we can do is the following. We can write it as 1 times 2 times 3 times 4 up to n. I'm actually going to work out 2 to the minus n times n choose n over 2. Because that way what is n over 2 factorial? It's all the numbers multiplied together from 1 up to n over 2. And then I got all numbers multiplied together from 1 up to n over 2 again. But if I have a 2 to the minus n there, I can multiply all those things by 2. So I'll get 2 times 4 times 6 up to n. I'm assuming n is even, because otherwise there's n over 2. Wouldn't be an integer, of course. So again, times 2 times 4 up to n. Now we've got a lot of cancellation. All the even numbers on the top cancel with half the stuff on the bottom. So we get 1 times 3 times 5 times 7 up to n minus 1 over 2 times 4 times 6 times 8 up to n. So far that's just equal to the quantity that we're trying to estimate. Now what I want to do is I want to square this. So let's have a look at the square of that quantity and get some bounds for it. Now I've got a half and I've got another half. So that's smaller than if I have a half and I replace the second one by 2/3. And similarly, I've got 2 lots of 3/4. That's smaller than what I'd get if I have a 3/4 and a 4/5. And I can carry on like that. This n minus 1 happening twice is going to be smaller than if I have 1 n minus 1 over n and 1 n over n plus 1. And what's this whole thing here? We've got a lovely telescoping product. Everything cancels except 1 over n plus 1. So I've ended up proving that this thing here, when I squared it, I got at most 1 over n plus 1. So I've got an upper bound of 1 over the square root of n plus 1. So it's certainly, I can, which is, in practice, of course, we would just say 1 over the square root of n is good enough. And I can use exactly the same trick. Let's just put this quantity is greater than or equal to. Oh, this lovely program gives me more paper if I'm running out. That's rather nice. So this is going to be slightly cleverer, but I'm going to say that this a half squared, I'll just have a 1 over 2. And I'll put another 1 over 2. Is that what I wanted to do? So 3/4, 2/3. Yeah, that's what I'll do. So that's just equality so far. Now the 3/4 squared is greater than or equal to what I'd get if I put 2/3 times 3/4, because I've replaced one of the 3/4 by a smaller fraction, 2/3. And then the 5/6 is bigger than if I put 4/5 times 5/6. And then I carry on like that. N minus 1 over n squared is bigger than n minus 2 over n minus 1 times n minus 1 over n. And now let's have a look at what cancels. I've got this 2 cancelling, this 3 cancelling, and so on, all the way up to the n minus 1 cancelling. So the only things that didn't cancel were that 2 there and that n there. So that's 1 over 2n. And so finally, what I've proved is that 1 over the square root of 2n is less than or equal to 2 to the minus n. N choose n over 2 is less than or equal to 1 over the square root of n, or if I really want, 1 over the square root of n plus 1. And you can do a bit better than this if you want to, but the thing that's often really useful is just that this quantity, or that this binomial coefficient is about 1 over root n times 2 to the n. So it's about 1 over root n of the total sum of binomial coefficients is concentrated in the middle there, which is of some interest, for example, if you want to understand better what the conclusion of Sperner's theorem is saying, for example. it's not that surprising that you should get around root n, and the way to see that is to think about a random walk. So what is n choose n over 2 times 2 to the minus n? It's the probability that a certain random variable is 0, and that's when the random variable is x1 plus, I'm just writing down what a random walk is, a one-dimensional random walk. And here we have xi equals 1 with probability a half, and minus 1 with probability a half, and they're all independent. And if we work out the variance of x, well, these are independent and they each have variance 1. So the variance of x is n, so the standard deviation is the square root of n. So the standard deviation of x is root n. So we sort of expect it to be mostly concentrated. We kind of know the distribution is going to look a little bit like a normal distribution. Most of the action takes place between, in a range of sort of round about root n. So we would expect the probability of being 0 to be round about 1 over root n, and that is indeed what happens. Of course, this idea can be explored in much more detail, but I just want to explain why the middle layer being about 1 over root n of the total is a very, very natural phenomenon. What else? Well, maybe another really, here's a very simple estimate actually. So supposing I want to look at other binomial coefficients. Let's have a look at nm, n choose m. So one bound that seems rather embarrassingly simple, but is actually surprisingly useful sometimes, is that it's at most n to the m. Why is that? It's because it's equal to n minus 1, n minus m plus 1 over m factorial. So if I just ignore the m factorial and observe that all of these things are at most n, I get this bound here. If you're a little bit uneasy about that, then why don't we just say, well, we know that m factorial, let's go back and see what it is. It's at least m over e to the m. So this must be at most, we can improve the bound if we want, and say it's at most n over m over e to the m, which when I do the calculation, get en over m to the m. So sometimes that's the sort of level of accuracy you want. Sometimes this will do. And sometimes this dividing by m is quite helpful. Sometimes we want more still. So even this bound stops being useful when m gets to be close to a half. Sorry, when it gets to be close to n over 2. And then we want something a bit better. So I'll talk a little bit about what happens then in just a moment. But another thing I want to talk about, which again comes up quite a lot, is ratios of binomial coefficients. And these we don't estimate, we just work them out exactly. So what is n choose k minus 1 over n choose k? It's quite nice not to have to write everything down. So the way to think about it is, let's just think about what is missing from the bottom on the top, and what's missing on the top from the bottom, so to speak. So we've got an n factorial on the top and bottom, so there's nothing missing from either. Here we've got a k factorial, and here we've got a k minus 1 factorial. So there's a sort of k missing, but it's a k missing on the bottom of this. So we end up with a k up on the top. We've got a sort of extra k on the bottom of the fraction down here, so it ends up on the top. And here we've got an extra n minus k plus 1, because this, the sort of, here we've got an n minus k factorial, and here we've got an n minus k plus 1 factorial. So we end up writing n minus k plus 1. And in particular, if, well, actually, that sort of is quite useful to say that's less than or equal to k. It's a slight shame that it turns out to be n k over n minus k plus 1, because it's not quite as nice as it would be if it was k over n minus k, but at least we've got an upper bound of k over n minus k. And to give an example of how that can be useful, let me just do a rather rough and ready estimate for the binomial coefficient n choose a half minus theta times n. I'm going to be a bit lazy and just assume that what I write down is an integer, because I can choose an integer here and then define theta accordingly. So I'm assuming also that theta is greater than 0. And what I'd like to show is that if theta is some fixed constant, this binomial coefficient is going to be much, much smaller than 2 to the n. And the way we'll do that is to say the following. Let's look at the binomial coefficient n a half minus theta over 2 n. I'll just hope that that's also an integer. Which all I'm really going to use about this is that it's less than or equal to 2 to the n. Now, what can we say? I want to put in something here. Now, I've got a sequence of binomial coefficients running from this one to this one of length theta n over 2. And for each one, the ratio is going to be at most k over n minus k, where k is the sort of thing on the bottom. So it's going to be at most a half minus theta over 2 divided by a half plus theta over 2. And then I'm going to be multiplying raising that to the power theta n over 2. So what I'm saying here is that when I go down from here to here, I'm going to be multiplying by something which I get from here by substituting a half minus theta over 2 for k. I will get this ratio or less, at least theta n over 2 times. And so I get something like this. And so let's get rid of that. So what about this thing here without the power? Let's just, well, no, I'll have the power. So it's 1 minus theta over 1 plus theta to the theta n over 2, which I'm going to be very sort of unambitious and say that's less than or equal to 1 minus theta to the theta n over 2 because the bottom is bigger than 1. And that's less than or equal to e to the minus theta squared n over 2. And if that last step wasn't clear to you, another extremely useful estimate is just 1 minus x to the t is less than or equal to e to the minus tx. Okay, so we conclude from that the original binomial coefficient, let me write it again, n choose a half minus theta n is less than or equal to e to the minus theta squared n over 2 times 2 to the n. So once you get away from the middle layer, the binomial coefficients become very, very much smaller than the total number, the sum of the binomial coefficients. So this factor here is far smaller than the 1 over root n that we had before, at least when n is large. Okay, now I'm actually going to show you something else that gives another proof of this statement with perhaps even a slightly better bound. So another rather useful fact is concerns sums of independent random variables. So I'm going to take some independent random variables. Independent, taking values in minus 1, 1, and all of mean 0. Everything I'm writing here can be generalized, but this is the form that I want to deal with because that's what I think that's all I'm going to need in this course. And once I've shown you the proof technique, you'll be able to generalize it if you need to. So what I would like to work out is the probability. Well, let's have, for convenience, x equals the sum of the xi's. I'd like to work out the probability that x is greater than or equal to epsilon n. And what I want to show is that this probability is extremely small. When n is large, I'm assuming, of course, epsilon is some fixed positive constant. Now, there's a trick for doing this and doing lots of other results of this kind, which is to work out something called exponential moments and then to use Markov's inequality. So if you want to know what that is, if you don't know what it is, then just watch on and you'll see. So we're going to consider the following quantity. We're going to consider the expectation of e to the lambda x. And the independence is going to allow us to do all sorts of nice things to this. So that expectation is, of course, expectation e to the lambda sigma xi. That's by definition. And by properties of our friend, the exponential function, that is the expectation of the product of e to the lambda xi. That's a product over I. And now we're going to use independence. Independence will, because these random variables are also independent, and so the expectation of their product is the product of their expectations. Now let's have a look at this quantity here for a particular I. So we'll have average of e to the lambda xi. Now I'm going to expand in a power series. So it's the average of 1 plus lambda xi plus lambda squared xi squared over 2 plus, I'll write one more, lambda cubed xi cubed over 3 factorial plus, and so on. And we can get rid of one of these because xi had mean 0. So bye-bye that one. But also, we know that xi takes values in -1, 1. So the absolute worst that we could possibly get here is 1 plus lambda squared over 2 plus lambda cubed over 3. And let's assume that lambda is less than or equal to 1. So added extra assumption. That's less than or equal to 1 plus lambda squared. That's not hard to check. Which is in turn less than or equal to e to the lambda squared. So we get that the expectation of e to the lambda x is less than or equal to e to the n lambda squared, because it's the product of these things. So now let's have a look at the probability that x is greater than or equal to epsilon n. Well, that is because x is an increasing function. I'm assuming lambda is positive, so it's the probability that e to the lambda x is greater than or equal to e to the lambda epsilon n. But because the average is at most e to the n lambda squared, that's certainly at most e to the n lambda squared divided by this. That's what Markov's inequality tells us. And I'm now free to choose lambda. Everything I've said was true for any lambda as long as it was between 0 and 1. So pick the one that minimizes this, which turns out to be lambda equals epsilon over 2, to get e to the minus epsilon squared n over 4 was an upper bound for that quantity. And there are proofs that do things a bit more cleverly and get better bounds for this. All I mean there is a better constant than 1 over 4, but that's good enough for our purposes. So now let's go back to binomial coefficients. So I'm actually not going to work out just an estimate for binomial coefficients. I want to work out an estimate for a sum of binomial coefficients. Let's also, by the way, just note that what we've proved so far, just by looking at minus x instead of x, we get that the probability that x is less than or equal to minus epsilon n is also less than or equal to e to the minus epsilon squared n over 4. Now, I want to look at the sum of binomial coefficients n choose 0 plus n choose 1 plus all the way up to n choose a half minus theta n. But what is that? That is exactly the probability that this random variable x is less than or equal to minus 2 theta n. That's because, sorry, I need to say that what I just said was rubbish, but if I put a 2 to the minus n in front, it becomes non-rubbish. So this thing here would be the probability that a random variable that takes values 0 and 1 is at most a half minus theta times n. But then if you change the 0 and 1 into a minus 1 and a 1, then it transforms to this inequality. And so by what we just proved, that's less than or equal to e. So I'm going to substitute 2 theta for epsilon, and we'll get e to the minus theta squared n, which is actually a better bound than what we had above, which was e to the minus theta n squared over 2, just for a single binomial coefficient. I've got e to the minus theta squared n for a whole sum of binomial coefficients. So as I said before, the sum of binomial coefficients is not that much bigger than the biggest one, so that's not as good an achievement as it might look. Okay, so that'll be another useful bound. I'm wondering whether I had anything else to say here. I think I just want to make one final remark, which is that it is useful to have a slightly better bound for n choose alpha n. And we shall see later on that that is pretty close to 2 to the h alpha n, where h alpha equals alpha log 1 over alpha plus 1 minus alpha. This is just a preview. Don't worry about this too much at the moment if you don't want to. Plus 1 minus alpha log 1 minus alpha. This is called the entropy function. You can get that by just plugging in estimates for factorials, and we'll get something like this, give or take some factor that's at most polynomial in n, which is good enough for many purposes. If you use Stirling's formula, you can get that it's this really to quite considerable accuracy. But I think I will now leave it there, and in the next video, we shall see how to apply some of these results, or we shall apply some of these results, and in fact we'll be applying these sorts of estimates in many places through the course. But that's it for now.